Now let's see whether we can use the principle of communicating vases with the sum of digits function. So here's the original sum of digits that we defined using the old technique. So how can we use the principle of communicating vases with some digits? So we have to find something that decreases, gets smaller, less computation, and another thing that increases, that gathers the result, accumulates the result. Well, sum digits works on digits of a number. So it seems reasonable that we need to have something that uses the representation of a number as digits. So let me bring in a diagram here. So each recursive call handles one digit. Now, this is already the case for the old definition. Well, let's divide the number n into its digits. So n is dk minus 1, dk minus 2, d2, d1, d0, and di is a digit from 0 to 9. So n has k digits. Let's now call the sum of digits function s of n, just to make sure we can have a simple formula. Then we can divide up the work as follows. When we're going through the number, we're gathering digit by digit. Well, after a certain time, we have here the number that still has to be done, and here are the digits that we have already gathered. So you see here we have gathered from 0 to I minus 1. So I digits have already been accumulated, and here we have k minus I digits that still remain to be done. Okay, so let's call this left-hand part S sub I, and the right-hand part A. So S sub I is the work that we still have to do, is the recursive part, in fact. And A is what we have already done. So in order to keep this formula true, when we make the step, now we have to make the step where the work still to do decreases and the work already done increases. So here, in order to make the step, I has to increment. That will make one less digit here. So I prime will be equal to I plus 1. And the di that is left out then becomes part of A. So A prime will be A plus di. And in that case, when I is equal to k, in that case, this is empty. There's no more digits here, so the value is 0. We have S sub k, which is S of 0, which is 0. Then A is the answer. Okay? That's how we can do it. That's how we can divide the work into two parts. So let's show an example again, analogous to the factorial function. So let's take the value of n that we've used already, 314,159. So we start here. S of 314159 is S of 314159 plus 0. So S sub I is this left-hand part, and 0 is the A, the right-hand part. So now we remove one digit, which is this number, 314159 modulo 10. This gives us the digit 9, and we do a div 10, giving this number 31,415. And then we continue. We do again modulo 10, giving 5. So the 5 plus 9 gives 14, and letting us 3141 that left over, and so on. We go from 3141 to 314, adding the 1 into A, and so on. We add the 4 in, we add the 1, we add the final 3, and here we've come with S of 0 plus 23, which is 0 plus 23, which is 23, which is the answer. Okay? Now let's use this idea to write the function, to write a second implementation, a more efficient implementation of sum digits. Okay, so as before, the two parts that we divide the function in have to be the two arguments. Now let's call them S and A. So if S is equal to 0, now remember S is S sub I, and when it's done, S sub k is equal to S sub 0 is 0. So F is equal to 0, then the result is A, else, and now we will look at our recursive call. Let's call these functions sum digits 2 and sum digits 2. So the S here is what? Well, it's S div 10. And so because we've removed one digit, and the A will be A plus what? Plus the last digit of S, plus S mod 10. So this gives us a new definition of sum digits. Let me define it here. Let me run it. Sum digits 2, 3, 1, 4, 1, 5, 9. And there's a second argument, the initial value of which is 0 in this case. We run this and we get, again, the value of 23. So you've seen, now we have a different function, a different kind of function from the original one, using the principle of communicating vases. And again, we can take this as an example of invariant programming. So what is the invariant? Well, let me bring back the diagram an instant. This is the invariant. S of n is equal to the s argument, here s sub I, plus the a argument. So that is, actually the s argument here is this, is the dk minus 1 to di, and the a argument is the accumulated digits. So the formula, invariant formula, then is this formula here, which is always true. Okay, this gives us an example of invariant programming. So the example is a little bit more subtle than the factorial function, but not by much. It's still quite a straightforward example where we can divide the work into two parts. We just have to focus on the right concept, which in this case is the digits of the number, in order to make the division easily. So again, we have one result, one part here, which accumulates, which gathers the result, and another part which reduces, it decreases the amount of work that has to be done.